All right, so hi everybody, and welcome back. Today we're going to be starting a new chapter, which is chapter 8 of the textbook. The topic here is potential energy and conservation of energy. This is a pretty substantial chapter. There's a lot to cover here, so we'll be taking our time. We're going to be spending the next 2 weeks on this topic. And before we jump into the lecture, I just want to remind you that as you go through the videos, you should be taking notes just like you would in an in-person class. So just make sure before we jump into this one that your notes are out and you're ready to go. So with that said, the first thing we need to cover is a distinction between what we call conservative and non-conservative forces. So let's define what these terms mean. Okay, so to introduce the topic here, I want you to think about an object that is moving in a closed path. So what we mean by a closed path is just that it starts and it ends at the same position. Now, while it's moving in this closed path, we're going to imagine that there's some kind of force acting on it. Okay, so here's the picture. We start here at some initial position, and then we move along a path. Now, this path can really be anything you want. It can be as complicated as you want, as long as, if we follow the path all the way around, we end up right back where we started. So there's your closed path. Okay, a few things to note. There could be some force acting on the object while it's moving. Okay, so that's what we call F, this vector. Also, this vector dr indicates a little bit of displacement along the path. Tiny little bit of displacement that you move as you go along this path. Okay, so what we're interested in is the total work done by that force, okay, for the entire closed path. And remember how this is going to work. W, that's the work done by our force, is given by the integral over that path. So F dot dr, if we integrate that and we put the limits as r initial to r final, just meaning initial and final position, if we do that integral, we'll get the work. So we're going to do this for 3 different cases. We're going to do it for the spring force. So in other words, we're going to imagine this force F is the spring force. We learned about that in the last chapter. In the second case, we're going to imagine this force is gravity. And in the third case, we're going to imagine the force is friction. Okay, so we're going to do those 3 cases. And then we'll notice that each one comes out a little differently, and that's telling us something about conservative forces. So this is where we're going. So let's take the first example, the spring force. A block is attached to a spring that rests on a frictionless table. The spring is compressed a distance d and then released. Okay, so here's what you should be picturing for the start. You're pushing the block in, so you're compressing the spring. So the value of x in this case would be minus d, and then we just let it go. So what happens next? Well, the spring is going to shoot outwards, as shown in the picture here, and at some point it's going to pass through x equals 0. Then it's going to overshoot that actually, but now the spring is going to be stretched out, so it's going to be slowing down as the spring stretches out. It will reach x equals positive d. So in other words, whatever distance you compressed it over here, it's going to reach that same distance but stretched out over here. And then after that, it's going to move back the other way. Okay, then it's going to move back this way. You're going to pass through x equals 0, and then you're going to end up back where you started. So this is exactly how we want to set this up. We want to imagine that the block moves over a closed path, so it starts and then ends at the same position. That's what we have here. So what we're going to do is calculate the work done by the spring force. Okay, so let's do that. And then the strategy for our calculation is going to be this. We're going to break the path into these 4 segments. The first segment, the one I'm labeling number 1 here, is we start at x equals minus d, that's over here. And then we go to x equals 0. That's the second picture. Okay, then the second part of the path is we're at x equals 0, and then we go to x equals d, which is over here. The third part of the path is we are at x equals d, and then we go back to x equals 0, that's over here. And then finally, we go from x equals 0 back to x equals minus d, which is over here. So that's how we break this closed path into 4 segments. So we're going to calculate the work for each one of these segments. That's the strategy. Okay, so to do the calculation, we'll just remember something we learned from the last lecture, which is for a 1D variable force. So we're only moving in one dimension, that's along the x-axis. And the force, the spring force, is variable. So we know that the work is going to be given by, integrate that force from some initial position to some final position. So x initial to x final. Okay, in this case, the force is given by Hooke's law, so that's going to be minus k times x. And again, x initial to x final will be the limits of integration. So how do I integrate that function? Well, k is a constant, and if I integrate x, that gives me 1/2 x squared. So I have minus 1/2 times the constant k times x squared. That's what I get when I integrate. And I evaluate that from x initial to x final. So in other words, I have minus 1/2 times k out front. I'll plug in x final, but I have to square it. And then minus x initial, but you also have to square that. Okay, so that's how this works. So all we need to do next is look at those segments of the path. Segment 1, remember, was x initial is minus d. That's when the spring is compressed by a distance d. And then x final is 0. That's when we reach the middle point. So then when we plug this in to get the work, let's say work for segment 1, W1, I'm going to have minus 1/2 k. Now x final is 0, so I have 0 squared here. And then x initial is minus d, so I have minus d squared, but I'm subtracting that, okay? So what are we left with? Well, if you square a negative, the negative sign goes away. But I have this negative sign, which is still out there. And then I have this negative sign. So overall, I have a positive sign. And I have 1/2 kd squared. Okay. What about segment 2? That's when we go from x initial is 0 to x final is positive d. Okay, so let's call this the work for the second segment. I'm going to have 1/2 k. And again, I just need to, minus 1/2 k. And I just need to plug in the values of x final and x initial. X final is d, and I square that. X initial is 0. So I have minus 1/2 kd squared for the work done in the second segment. Moving on to the third, this is where x initial is plus d, and then x final is 0. So the work done by the spring in that third segment is minus 1/2 k. Plug in 0 for x final, and then plug in d for x initial. So again, we have these two negative signs which cancel to give you positive 1/2 kd squared. And then finally, for segment number 4, we're going from x initial equals 0 to x final equals minus d. So the work done in the fourth segment is minus 1/2 k. My x final is minus d, so I'm going to square that guy. And my x initial is 0. Okay, so overall, when you square the negative right here, it goes away. But I have this negative sign out front, so I have an overall negative sign, minus 1/2 kd squared. Okay, so the total work for this closed path is W1 plus W2 plus W3 plus W4. So basically add these 4 numbers together. Well, plus 1/2 kd squared minus 1/2 kd squared, those cancel. And then these also cancel. So we get 0. Okay, so just keep that in the back of your mind. The spring force has this property to it where if an object moves in a closed path, the total work done by the spring force is 0. Okay, so the result of the work we just did is that W total, which is, the sum of these 4 different terms for work, is equal to 0. And again, what that's saying is the total work done by the spring force over this closed path where we start and end at the same position, that came out to 0. The second case we're going to look at is gravity. So again, we want to imagine an object is moving while gravity is acting on it, but it moves in a closed path, so it starts and ends at the same place. A really simple example of that would just be throwing a ball straight into the air and then waiting for it to come back down to its starting position. So that's what we're dealing with. A ball is thrown straight up into the air. It reaches some maximum height. Let's call that h. So this is the maximum height we reach. And then it falls back down to its original height. So we're going to take that overall motion and we're going to break it into 2 segments. Okay? So segment 1 is just the upward motion. So we start at y initial, so a height of 0 down here. And then we end up at a height y final of h. Okay, so that's just whatever that height is. The second part of the motion we'll look at is the downward motion, where we start up here at y initial is equal to h, and then we end up down here at y final is equal to 0. Again, the strategy is we want to calculate the work done by gravity for those 2 parts of the motion. So let's work it out. Okay, so I'm going to bring back another fact that we learned back in chapter 7, which is that for constant forces, the work can be written as W times D cosine phi, so we don't actually have to do any sort of integral. F, of course, is just the magnitude of the force. In this case, we're dealing with gravity, so that's m times g. D is the distance you move, and phi is the angle between force and displacement. Okay, so for the first part of the motion, when we're moving up, let's actually draw the ball moving up. Okay, so its displacement is this way, but the force is down. So it's moving up, so the displacement is up, but the force of gravity is pulling it down. So what would be the angle between force and displacement? Well, they're exactly opposite each other, so the angle between them is 180. Okay, so therefore, the work done during the first part, when we're moving upwards, is going to be the force is m times g. The distance we move is just h, whatever that height is, and we'll have cosine of 180. Now, cosine of 180, you should know, is -1, so we have minus mgh. So gravity is doing negative work, which makes sense. It should be slowing the ball down as it moves upwards. Okay. The second part is when we're moving down. And we can draw the picture of the ball again. The force of gravity doesn't change. It's still pointing straight down. But since we're moving down, the displacement is now down. And so the angle between force and displacement is 0 degrees this time. They're pointing in the exact same direction. And so the work done for this second part of the motion is the force. The magnitude is mg. The distance we move is h. We move that same distance h on the way down. But now we have cosine of 0. Cosine of 0 gives you positive 1. So here, cosine 180 was -1. Cosine 0 is positive 1. So we have positive mgh for the work done by gravity as the ball is going down. It makes sense it comes out positive because if you have the ball falling down now, it's speeding up. Okay, so we expect positive work. The total, which is W1 plus W2, well, these two just cancel each other out. The work done on the way up is canceled out by the work done on the way down, so it gives you 0 total. So notice this is kind of similar to the spring force in that the total work done by gravity over this closed path is equal to 0. Okay, and this is the result that we were getting at, that W total, which is the sum of the work 1, which is on the way up, plus work 2 on the way down, gives you 0. So again, like the spring force, the total work done by gravity over a closed path comes out to 0. All right, so the third example is friction. Let's consider an object that's moving in a closed path. So it comes back to where it started, and that whole time friction is acting on it. So the scenario that you can have in your head is this. Let's say we have a puck, like a hockey puck, and it's connected to a string, and the point of attachment of that string is right here. So this is a fixed point of attachment. And the puck is moving in a circle. The radius of that circle is r, and it's moving on a flat table. So we're looking in this picture at a top-down view of the table, and we're seeing the puck move in this circular path. Okay? But we're imagining that there is friction between the puck and the table, and the coefficient of kinetic friction is going to be mu k. So again, the goal here is to find some kind of expression or formula for the work that's done by friction over this entire path. So let's work it out. Okay, so what we're going to be doing here is thinking about the work done by kinetic friction. And the way this force works is it's given by the equation F sub k is equal to mu sub k times n. That's kinetic friction force. Okay, next, let's think about the distance that our object is moving. So remember, this hockey puck moves in one complete circle. So the distance traveled would be the circumference, which is equal to 2 pi times r. That's how you calculate a circumference. Okay, next. Let's think about the angle. By the way, the formula that I want you to be thinking is work is FD cosine phi. So we've basically described what the force looks like. We've described the distance moved. Now let's think about the angle phi. Well, this is an angle between your force and your displacement. So let's draw that hockey puck. Let's look at it from the side. Let's say the hockey puck is moving this way from our point of view. Well, we always know friction is going to be opposing that motion. So at all times, the angle between the force and the displacement right here is going to be 180. Okay, so we know that as well. So then what is the total work then for one complete circle? Well, we take the force, which we said is mu k times n. We take the distance moved, which is 2 pi r. And then we take cosine of the angle, which is 180. And we remember that cosine 180 just brings out a negative sign. So overall, we have a negative sign out front, and then we have 2 pi times r times mu k times n. And really, I'm not so concerned with this exact formula. I just want you to note that we did not get 0 this time. So it's not 0. So this force is a little bit different from the other two, because in the other two, we had an object that moved in a complete circle, came back to where it started, and the work was 0 for the closed path. In this case, we're not getting 0. So friction is different from the other two. Let's get into that. Okay, so what we just did is we calculated the work done by friction as the puck moved in one complete circle. And we found that W total is equal to negative 2 pi r times mu k times n. Again, the important thing is not so much the exact formula, but I want you to notice that the total work done by friction over this closed path was not zero. Okay, and so this takes us to the definitions of conservative and non-conservative forces. So the three examples that we did really help illustrate the difference between those two. So a conservative force is any force that has the following property. If an object moves in a closed path, the total work done by a conservative force on the object will be zero. Okay, so which examples did we see that were conservative forces? Well, the spring force is one because, of course, we saw that for an object that moves in a closed path, the work done by the spring force is going to be zero. And the same holds true for gravity. If an object moves in a closed path while gravity acts on it, the total work done by gravity is going to be zero. But friction was an example of a non-conservative force because it doesn't have this property. We found that if an object moves in a closed path while friction is acting on it, the total work is not going to be zero. And another example would be air resistance. So friction and air resistance will be the two non-conservative forces that we encounter most often. So just remember, friction and air resistance don't have this property, so we call them non-conservative. Okay, there's also a different way you can think about conservative forces and what makes something a conservative force, and that is path independence. Okay, so the work done by a conservative force only depends on the starting point and the end point. It doesn't depend on the specific path that you take. So let's look at an example. Okay, let's say point A is where we start the motion, and then point B is where we end up. So you can imagine all kinds of different paths that start at point A and end at point B. You could take path 1, shown here. You could take the straight line path if you want, that's path 2. You could also take this one down here, that's path 3. That's like the scenic route. And the point is, if you have a conservative force, the work is going to be the same for all three of those paths. So W1, W2, W3 will all be the same as long as you have a conservative force. Of course, if you have a non-conservative force like friction or air resistance, then there would be a different amount of work being done for each of these paths. Maybe path 1 is different from path 2, is different from path 3. But again, if you have a conservative force, it's path independent. Doesn't matter what path you take. All that matters is where you start and where you end up. Okay, so to make sure we understand the difference between conservative and non-conservative forces, let's take a look at an example problem. So in this problem, you're trying to push a box across the floor at a constant speed, and you start over here at point A, and you want to end up over here at point B. So you want to move the box from point A to point B, and this is what it looks like from the top-down view. All right, so there is friction between the box and the floor, meaning you're going to have to fight against that friction force as you push it. Which path is going to require you to do less work? Path 1 or path 2? And then as a follow-up, can you consider the force that you exert to be conservative? Why or why not? So think about this for a second, pause the video and see what you come up with, and then come back to it. Okay, so the first thing to see is that if we're trying to counteract friction to get the box moving, we need to apply an opposing force. So in other words, you're pushing the box forward in the direction that you're trying to move it, but friction is pushing back in the opposite direction. So you're providing an opposing force, in other words. And the thing we know about friction is that it's non-conservative. So that automatically makes your opposing force non-conservative. okay? So non-conservative. And the thinking behind this is the amount of work you do is going to depend on the path. Okay, so we have two paths, right? We have path number one, which is kind of this half circle shaped path. And then we have path number two, which is just the straight line. So we're not going to be doing the same amount of work if we push along these two paths. In fact, the work we would do pushing along path number one would be greater than the work along path number two because of the greater distance. Because here, path one involves a greater distance. Again, that's something you know intuitively, that this would take less work, right? But that can be now expressed in terms of this new vocabulary of conservative and non-conservative forces. Okay, so now that we've come up with these definitions for conservative and non-conservative forces, we can put them to use and start talking about potential energy. So as an introduction, I want you to think back to the previous chapter where we encountered another type of energy called kinetic. And kinetic energy is given by uppercase K. The formula for it, if you remember, is 1/2 mv squared, where v is the speed of the object. So if v is equal to 0, it has no speed, it's not moving, then k is equal to 0. If v is a really large number, then k is a really large number. But the point is, an object has kinetic energy because of the way it's moving. Okay, so it has kinetic energy by virtue of its motion. Kinetic energy depends on motion. On the other hand, potential energy is given by the variable uppercase U. And what we say an object has potential energy by virtue of its location. So potential energy doesn't depend on how fast your object is moving. It depends on where your object is located. So the exact formula for U is going to depend on some details like the forces that are acting on the object. So it depends on the situation, but it's always some function of position. In other words, you plug in a position and you get out some potential energy. That's how this will work. Okay, but remember, we have this thing called a conservative force. And for a conservative force, work only depends on the endpoints of motion and not the path that you take. Okay? So that means if we want to calculate the work for a conservative force, the way we would do this back in chapter 7 is to use an integral, right? We would have work is the integral of f dot dr, and we'd go from some initial position to some final position. We'd put those as our limits of integration. So you want to think of that as you're integrating over some path to get the work, okay? But if you have a conservative force, you shouldn't even have to do that, right? We don't even need to know what the path is. We just need to know the starting position and the ending position. We don't need to do this crazy integral. In other words, if I want to calculate the work done by a conservative force, I should just be able to plug initial position and plug final position into some formula, and the work should pop out of that formula. So this mysterious formula that I'm referring to here is called the potential energy. Okay, so next, let's develop how do we actually calculate potential energy in any given situation. And to sort of set this up and motivate it, let's take a look at a specific example, which is lifting a ball up into the air. So you have a ball, mass m. You start at some height y1 over here, and you end up at some height y2 up here. Pretty simple. We're also going to imagine that as you move the ball up, you move it very smoothly at a constant speed. So it's not, a jerky motion where the ball is speeding up and slowing down. You're just going to move it smoothly up at a constant speed. We know that in order to do this, you need to apply some kind of force. So we'll call that F lift. So you're pulling up with some force F lift. Gravity is pulling the ball down like this. And those are the two forces acting on the ball. Okay, so to do a little bit of work on the side here, this is the ball, again, F lift going up like this, and F gravity going down like this. And we can apply F equals ma, Newton's second law, to the ball. But the thing about the acceleration of the ball is we can immediately set it to 0 because the ball is just moving at a constant speed in a straight line. Okay, so therefore, on the left side of the equation, where we add the forces together, we have F lift plus F gravity, and I'm writing these in vector form, so add the two vectors together, and we get 0. What that tells me is that F lift is equal to minus F gravity. Another way of saying this is the forces are equal in magnitude, but they're pointing in opposite directions. That's what that tells you. So next I'm going to integrate both sides. So on the left side, I'm going to have F lift. I'm going to dot this with dr, which is a little displacement, and then integrate that guy. I'm going to do the same thing on the other side, and I'm going to pull the negative sign out. And again, I'm going to take F gravity, and I'm going to dot it with dr, and then integrate. It's totally fine to do that as long as you do it on both sides of the equation. Okay, but if I look at the left side, I should just recognize that if I'm integrating the lift force, okay, that's just the work done by the lift force. And on the other side, we have a negative sign, but I'm integrating the force of gravity over some path, and that's just the work done by gravity. So the point I'm trying to get across here is, as you lift the ball upwards, the work that's done by the lift force is just negative the work done by the force of gravity. So we're going to use that in a second. Okay, so what we just found is that during this motion of lifting the ball upwards, the work done by gravity and the work done by this lifting force are opposite one another. So in equation form, that says W lift is equal to minus W gravity. Another thing we can say about W lift, the work done by this lifting force, is that it gives the ball some energy. Remember, that's sort of the conceptual definition of work in the first place, is when you do work on an object, you're transferring energy to it in some way. So in this case, the ball is not actually changing in kinetic energy because it's moving up at a constant speed. So we're not transferring kinetic energy to the ball. Instead, we're transferring potential energy to the ball as we lift it up. And so an equation we can write down is W lift, the work we do, is equal to delta U gravity, the change in potential energy associated with gravity. Okay, and then we can take these two results and combine them to say, because I can, of course, replace W lift with minus W gravity. So if we do that over here, I'm going to have delta U gravity equals minus W gravity. Okay, what that's saying is the change in potential energy, delta U, for gravity, is equal to minus the work done by gravity. Now, delta U equals minus W is not something that just applies to gravity. It actually applies in general when we have a conservative force. Okay, so the general picture for potential energy is this. If you have a conservative force, and we'll call that f of x, okay, this means you plug in some value of x and a force pops out, there's going to be an associated potential energy function, which we'll call u of x. So again, it might also depend on position, might depend on x. And we define that as follows. We have delta U for the force, is equal to minus W, the work done by that force. Okay? So let's expand this out a little bit. On the left side where you see delta U, think of that as a final value minus an initial value. So we'll have U of X, that'll be our final value, minus U of X naught, that will be our initial. So we're using the subscript 0 for initial. If you don't see that, it means final. Okay, so we have final potential energy minus initial. That's how you read this. And then we have on the right side a negative sign to start off with, and then some kind of work. Well, the general way we calculate work is by integration, and we integrate the force basically to get the work. So we'll take whatever the force is, f of x dx, and we'll integrate it between those same 2 points. So x naught down here and x up here, where again, these can be thought of as initial and final positions. Okay. So that position x naught is what we call our 0 point. Okay? It's defined as the position where the potential energy goes to 0. So the thing about 0 points is it doesn't matter what you choose for your 0 point. You're always free to choose the value of x naught where the potential energy goes to 0. You can set it wherever you want. So by definition, the potential energy at the 0 point, at the point x naught, is equal to 0. And so this term, potential energy at x naught, is going to go to 0. And then all we're left with is U of x, that's the potential energy function that we want, is equal to minus x naught, that's wherever you set the 0 point, integrate all the way to x, f of x dx. If you do that integral, you'll get the potential energy function. Okay, so by the way, this only works if you have a conservative force, okay? If you have a conservative force, you can find the potential energy function basically by integrating the force with a negative sign out front. If you have a non-conservative force, like friction, like air resistance, this doesn't work. You can't have a potential energy function for a non-conservative force. So that doesn't work. Okay, so before we get any further into the calculus behind potential energy functions, let's do an example. And the easiest example I could come up with is gravity. So we know from earlier in the lecture that the force of gravity is a conservative force, and that means that there's some kind of potential energy function that we can associate with gravity. So we want to find out what that is. So the first thing we have to do is remember how the force of gravity actually works. So as long as we're staying close to Earth's surface, okay, as long as we're not going way out into space and getting really far from the surface of the Earth, the force of gravity is constant and is given by m times g. And we put a little negative sign next to that just to indicate that the force is going down. Okay, the next thing we need to talk about is the 0 point. So the 0 point, remember, is just the position or the location where we say potential energy is going to 0. So you can choose any point you want, but the easiest thing to do is just to say the potential energy goes to 0 when we're at y is equal to 0. In other words, potential energy at position y equals 0 is 0. Okay, so we want to get a potential energy for gravity. And the way we'll do this, and this is the way we'll always start if we're trying to find the potential energy function, is to say that delta U is equal to minus W. But we'll put a little label, we'll say G, since we want to remember we're talking about gravity here. On the left-hand side, I have a delta, which you can think of as a final minus initial value. So we'll have UG at position Y, which is our final position, minus UG at position Y0, which is our initial position. And then on the other side, I'll have negative. Work is given by an integral. I go from the same two positions. So let's say y0 to y as our limits. And then I have the force. Okay, so Fg is a function of y times dy. So I'm using y instead of x here because, of course, gravity acts in the vertical direction rather than in the x direction. But it's the same general equation we saw earlier. And the next thing we'll do is bring in our 0 point. So let's set y naught equal to 0. That's just going to be our initial position in this case. So think we start off at ground level. And so on the other side, I'm going to have minus 0 to y. The force is minus mg. And then we have dy. Okay. But if we say the 0 point is at y equals 0, that means the potential energy at y equals 0 is equal to 0, meaning this term right here on the left side goes away. Okay, and we're free to set the 0 point wherever we want. So what we're left with is potential energy as a function of y is equal to, I have two negative signs on the right side, so it's a positive. And then mg is a constant, so that can come out. And then I'll have 0 to y integral of dy. Okay, well, we have constant mg out front. If I integrate dy, I get y. And my limits are 0 to y. So I'm going to have mg. Top limit is y, bottom limit is 0, so that's y minus 0. mgy is what we're left with. So gravitational potential energy is given by m times g times y. Okay, so using the definition, again, delta U is equal to minus W, we were able to work out the potential energy function, which is mgy. So in this case, m is the mass, y is going to represent the height of the object off of the ground, and g is the acceleration due to gravity, which is 9.8 meters per second squared. So notice, just like we said at the outset, the potential energy depends on position. It depends on y. So you plug in a value of y, and what you get is the potential energy out of that. That's how you interpret this. Okay, next, let's take a look at spring potential energy. This is sometimes also referred to as elastic potential energy. These mean the same thing. And we saw earlier in the lecture that the spring force is a conservative force. And that means there's a potential energy function that we can find and associate with it. So back in chapter 7, we learned about Hooke's law, which says that the spring force is given by minus kx. And the negative sign here just indicates that we have a restoring force. In other words, the spring force always brings the spring back towards equilibrium. That's what the negative sign tells you. Okay, so before we go and calculate the potential energy function for the spring force, we need to state what the 0 point is going to be. So the easiest thing to do is just to put the 0 point at the equilibrium position of the spring, x equals 0. Remember, when x is equal to 0, the spring is perfectly relaxed. It's not compressed and it's not stretched out. So what we'll say is spring potential energy when x is equal to 0 is 0. That's how we'll do it. Okay, so we start just like before with delta U is equal to minus W. And then we'll put a little s subscript on each one of those terms because we're talking about a spring force here. And then just like before, we can expand out the left side to say this is some kind of final value minus some kind of initial value. So spring potential energy at position x, that'll be final, minus spring potential energy at position x naught, that'll be initial. And then we have minus on the right side. The work is given by the spring force integrated from those same two positions, x naught to x. Okay, so that's how we expand the equation out. Okay, next, we're going to say, we're just going to say that x naught is equal to 0. We're free to set that value. So I'll have spring potential energy at x minus spring potential energy at 0 equals minus, now we're going from 0 to x, and our force is given by Hooke's law, that's minus kx dx. Next, we'll set the 0 point to be x equals 0, meaning, again, the spring potential energy, when you plug in 0, is going to be 0. So I can cancel that guy out. So our spring potential energy, as a function of x, it's going to be, okay, I have two negative signs on the right side. That's positive. K is a constant, so I can actually pull it out of the integral. And then now we're going from 0 to x dx. Okay, so I'm integrating x. This goes to 1/2 x squared. And my limits are 0 to x. Plug in those limits. I have k. The top limit, well, it's just x, so 1/2 x squared. But the bottom limit is 0. And when you plug in that, you get 0. So therefore, my spring potential energy is 1/2 kx squared. That's how that works. Okay, so what we've worked out using the same basic idea that delta U is equal to minus W, we get the result that spring potential energy is given by 1/2 kx squared. So again, the idea is you plug in some value of x for the spring, and again, x tells you how much the spring is compressed or stretched out. You plug that in, and it tells you how much potential energy the spring is storing. Okay, so x is the change in length from equilibrium. Just remember what that means in the equation. Okay, so let's take a look at an example where we can actually do some calculations with the functions that we derived. So at the end of a train track in a train station, trains are prevented from crashing into the platform by a bumper mounted on a spring. So here's the little spring bumper that brings the trains to a stop. And this is a really stiff spring, so really large K value. K is equal to 1.25 times 10 to the 8 newtons per meter. So if a train hits the bumper and it comes to a stop after compressing the spring by a distance of 5.6 centimeters, so it pushes it in by 5.6 centimeters before stopping, what is the potential energy stored in the spring at the moment the train stops? So you're going to use this to calculate potential energy. Let's see what you get. Okay, so we're going to use the result that spring potential energy as a function of x is given by 1/2 kx squared. And in this case, we can just sort of do a plug and chug because k is equal to 1.25 10 to the 8 newtons per meter. I just want to remind you that 1 Newton per meter is the same as 1 kilogram per second squared. I'm going to use that. And x is just the amount of compression or stretching that the spring undergoes. Now technically, since we're compressing the spring, this carries a negative sign. We have 5.6 centimeters, but we want to get this in meters. So 10 to the minus 2 meters is equivalent to a centimeter. And we square that. So technically, we need the negative sign in here to indicate that the spring is being compressed, not stretched. But it doesn't matter because you square that and you get something positive out anyways. So what you get is 1.96 times 10 to the 5th power. And let's take a look at what units we have. We have kilograms. We're going to get meters squared. and we're going to have seconds squared on the bottom. So 1.96, 10 to the 5. I hope you remember that a kilogram times a meter squared per second squared is equivalent to a joule. So what we're dealing with is 1.96 times 10 to the 5 joules. That's how much energy is being stored in the spring as a result of compressing it this way. Okay, let's go a little deeper into the relationship between potential energy and force. And we're going to bring in a concept from calculus called the fundamental theorem, which I hope you remember from your first calculus class. And basically what this says is that integration and differentiation are inverse operations. So let's see what that means. This is the most common way you're going to see the fundamental theorem written out. And this says that some function f evaluated at point B minus that same function f evaluated at point A is equivalent to the integral from A to B of df dx times dx. Okay, so let's just see what the concept behind this equation is. Well, we have a derivative of f right here, df dx, and then immediately we're integrating that. Okay, so on the right side, just think you take a derivative and then you integrate that derivative. Well, on the left side, you just have the function f. So what this is saying is that if you take a derivative and then you integrate a function, you just go right back to the function f you started with. That's another way of saying, again, that taking an integral and taking a derivative are inverse operations because one sort of undoes the other. Okay, so let's apply that idea to what we know about potential energy. We know that potential energy is found by integrating a force, but of course there's a negative sign out front. So if that's the case, then we should be able to find the force by taking the derivative of potential energy, okay? So in other words, if you can integrate the force to get potential energy, you should be able to take the derivative of potential energy to get the force. And then just remember there's a negative sign out front. Okay, so in equation form, this says the force f of x is equal to minus du dx, because again, that negative sign is always out front. And let's see if this actually works, because we have two examples of potential energy functions that we've derived so far. So how about for each one, gravity and the spring potential energy, take the derivative with the negative sign out front, and then see that you get the force back when you do that. Okay, so pause the video, take a few minutes to do those derivatives and just verify that this works. Okay, so if we take the case of gravity, we know that our potential energy function, gravitational potential energy as a function of y is equal to mgy. So we should therefore expect, if what I said is true, that the force of gravity as a function of y would be minus the derivative of that potential energy with respect to y. Okay, so I have minus d dy, that's the derivative of mgy. And then we'll remember that whenever we calculate a derivative, we can pull out constants. Mg are both constants. So I have minus mg out front, and then I have the derivative with respect to y of y, which is just 1. So we're left with minus mg, which is the original force we started with. So it works. Okay, what about for the spring potential energy? Well, we have the potential energy function is a half times kx squared. And again, the idea should be that the force as a function of x should be minus the derivative of the potential energy with respect to x. And so we have minus the derivative of 1/2 kx squared. And just like before, we can pull out anything that's constant, which would be the 1/2 and the k factor. There's also a negative sign out there. And I'm taking the derivative with respect to x now of x squared. So what I have is minus 1/2 times k. What's the derivative of x squared? Well, you bring the 2 out to the front, and then you reduce the power by 1, so that's just 2x to the first power. Or if we simplify that, 1/2 cancels with 2, so I just have a negative sign, and then k times x, which again is the original force that we started with, so this does work. Okay, so let's take a look at this example here, where we have an object that's moving in one dimension along the x-axis, and the object's potential energy is given by this function, u of x, where u is the potential energy in units of joules, and x is a position in units of meters. So u of x is 4x to the 5th minus 2x to the 3rd plus 5. So the question is, what is the function that describes the force? What is f of x? And then what would the numerical value of the force be in newtons when the particle is located at x equals 0.50 meters? So pause the video, try to work this one out, and then we'll go through it together. Okay, we'll start by just copying down the potential energy function. U of x is 4x to the 5th minus 2x to the 3rd plus 5. And we know that if we want to find the force, f of x, that would be minus du dx. So take the derivative of that function u, and then just put a minus sign out front, and you have the force. So the force is minus the derivative, d dx, of 4x to the 5th minus 2x to the 3rd plus 5. So we have a minus sign out front. If we take the derivative of the first term, what happens is we take the power of 5 to the front, where it multiplies the 4, and we have 20. And then the power gets reduced by 1, so we have 20x to the 4th. Okay, for the second term, the power comes out to the front, so we have 3 times 2, which is 6. And then the power gets reduced by 1, so we go from x to the 3rd to x to the 2. And then finally, the last term is just a constant. So if we take the derivative of just the number 5 with respect to x, we're going to get 0. So therefore, what we have is minus 20x to the 4th plus 6x squared. So we can plug in a value of x, we can plug in a position, and then the force at that position will pop out. So if we want to know the force at x equals 0.5 meters, we're going to have minus 20, 0.5 to the 4th, plus 6 times 0.5 squared. And if you do that calculation, what you'll get is 0.25. Units are newtons here. And it's positive, indicating the force is in the plus x direction. So that's how that works. All right, so the last thing we need to talk about before we go into the next section is that potential energy is relative. So what do we mean by this? Well, only changes in potential energy have any kind of physical meaning. That's the idea. The actual value of this function at any given point is totally arbitrary. It doesn't really matter what the value is. All that matters is how it changes as you go from one place to another. So to flesh this idea out, let's say we have some kind of function u of x for potential energy. We know that the associated force, f of x, is just minus du dx. Okay, so what happens then if we added a constant? So now imagine our function is u of x plus c, where c is just any kind of constant you want. So by doing this, we've changed the actual value of u everywhere, okay, because we've added a constant to it. And the associated force would be minus the derivative of this whole thing, which is u of x plus c. So that can be split into two terms, where we have minus d dx of u of x, and then we have minus d dx of c, this is just saying take the derivative of a constant, which we know is going to go to 0. Just cross that one out right away. So all we're left with is minus du dx, which is exactly where we were before we added a constant. So in other words, adding that constant didn't change anything about the force that's being described. Nothing at all whatsoever changed in terms of the physical force being described. So you're perfectly free to add any kind of constant to your potential energy function. It won't really change anything about the physics. And that's equivalent to saying that we're free to set the 0 point of the potential energy anywhere we want. In other words, we can define the point in space, the position, where the potential energy goes to 0 to be anywhere you want, okay? So you're free to add a constant. You're also free to set the 0 point anywhere you want. That's how these functions work. Okay, so the next topic is conservation of mechanical energy. So first, we'll define mechanical energy, what this term means. So in equations, you're going to see this as the variable capital E, that stands for mechanical energy. And it's really just the sum total of potential and kinetic energies in whatever system you're looking at. So E, that's mechanical energy, is equal to K. That's kinetic plus U, that's potential. That's the definition. So the reason we care about mechanical energy is under certain circumstances, it can be conserved. So remember, in physics, when we say a quantity is conserved, it just means it's not changing over time. So as long as we have a system where there aren't any non-conservative forces doing work, so we don't have things like friction or air resistance that are doing work on the system, that's what we mean. Okay? WNC, W non-conservative is equal to 0. As long as that's the case, then mechanical energy is conserved. So there are different ways we can come up with an equation that says mechanical energy is conserved. A really simple way to say it is delta E is equal to 0. Okay, another way to say it is E initial is equal to E final. So if you compare the value at some initial time and some final time, it will stay the same. Or we can say delta K plus delta U is equal to 0. So this delta E is equal to 0, and this down here, E initial is equal to E final, and this delta K plus delta U is equal to 0 are all different ways of saying the same thing. Mechanical energy is conserved. And it's going to be true as long as this is true, as long as, again, there aren't any non-conservative forces, like friction or air resistance, doing work on the system. Okay, so to flesh this out a little bit more, let's start with the definition of mechanical energy. E is equal to K plus U, kinetic plus potential. Okay, so if conserved, then we have delta E. The change in mechanical energy should be 0. That makes sense. It's not changing. So when we see delta E, that's just E final minus E initial. So if that's equal to 0, then E final is equal to E initial. So that's one way to state the problem, or to state the idea that mechanical energy is conserved. Okay. So if delta E is equal to 0, then well, that means delta K plus U is equal to 0. In other words, delta K plus delta U is equal to 0. So this is yet another way to state, that should say, here, let's go back. Delta K plus delta U is equal to 0. This is another way of stating mechanical energy is conserved. Okay, so let's take a look at a conceptual example of conservation of mechanical energy. So what we have here is a block and a spring. Pretty simple system. The block is initially sliding to the left along a surface with no friction, and also let's assume there's no air resistance either. And then the block runs into a spring over here, it will initially compress the spring and move to the left, but it's going to slow down as that happens. Eventually it will come to a stop, and then it will be fired back out by the spring and go to the right. So what we can look at is the kinetic energy of the system. That has to do with the way the block is moving, how fast it's moving. And the potential energy, that has to do with how much the spring is compressed. The more it's compressed, the more potential energy we'll have. So initially, it's all kinetic. The spring is perfectly relaxed, there's no potential energy, and the block is just moving along to the left, and it has some kinetic energy. But let's look what happens, when we play the video. Okay, so while the spring is being compressed, you see kinetic energy is decreasing, potential energy is increasing. Let's see it again. But it happens in such a way that the sum total of K and U stays the same. That's what we mean by mechanical energy is conserved. So you can trade a little kinetic energy for a little bit of potential, that's fine, but it's the sum total that's staying the same in this process. If you want to take a look at the animation at home, there's a link to it right here. I took it from this website, brilliant.org, so check that out if you want to. And again, it's worth repeating that mechanical energy would not be conserved if we had friction or air resistance. Okay? So we can look at another conceptual example similar to the one we just saw. We have a roller coaster with a cart that's going to move along the roller coaster track. Okay, so we're going to make some assumptions. We've got no friction and no air resistance. And also, the cart is not being propelled by any kind of motor. Okay, so it's only gravity that's making the cart move. Okay, so we'll just sort of let it drop from this point and then move under the influence of gravity alone. That's the idea. So we have potential energy. This time, it's gravitational potential energy. It has to do with how high off the ground the cart is. And then we have kinetic energy. So let's see the animation play out. Okay, so notice what's happening. As the cart descends, the potential energy decreases and the kinetic energy increases. But then as the cart goes back up, the potential energy increases and the kinetic energy decreases. But the sum total of those two, K and U, is going to stay the same. Again, that would not be true if we had friction or air resistance or if the cart was being propelled in some way. But in this situation, we have mechanical energy being conserved, and we can use that to make predictions about how the cart is actually going to move. So this is how we actually apply the idea to solve problems. So conservation of mechanical energy can only be applied when you have WNC is equal to 0. So that means the process that is being described in the problem doesn't involve things like friction and air resistance doing work on your system, okay? We have to have this be the case if we're going to use conservation of mechanical energy. Okay, so what I would suggest is to make a table to keep track of all the relevant forms of energy in your system. So anytime you have a moving object in your system, you know you have some kind of kinetic energy to worry about. And if you have a conservative force that's acting on your system, you know you have a potential energy to worry about. So in your table, this is what it would look like. You would list every form of energy. So this is just an example. You might have kinetic and then gravitational potential and then spring potential, let's say. And then you would look at the initial state of your system and then the final state. So your job would be to fill in this table. Okay, you want either a number or a formula for the kinetic energy initial and then kinetic energy final. You'd fill those in. You do the same thing for the gravitational potential, and you do the same for the spring potential. So if we want to say that mechanical energy is conserved, then the sum total of all the energies in your initial column here have to equal all of the energies in your final column. That's how we apply the idea. So the equation we're thinking about is E initial, which would be, again, all of these energies in the initial column added together, equals E final, all of these added together. Equivalently, we can say delta K plus delta U is equal to 0, but you might have multiple delta Ks if you have multiple moving objects. You might have multiple delta U's if you have multiple forms of potential energy. Okay, so let's take a look at an example where we can start to put these ideas to use. So we have a rock thrown off the edge of a cliff, which is 140 meters tall, and it's thrown with an initial speed of 25 meters per second. What is the speed of the rock in units of meters per second when it reaches the ground over here? So we're going to ignore air resistance for this problem. Pause the video, try to work it out, and try to use that method I showed you where you create a table to keep track of the energies. See what you get, and then we'll go through it together. Okay, so let's set the problem up by first taking note of what's going on in the initial state. This is when the rock is thrown from the cliff. And so what do we know in the initial state? We know the speed is 25 meters per second, that's V initial. We know the initial height is 140 meters. Then in the final state, this is when the rock is just about to hit ground. We don't know the final speed. That's what we want to find in this problem. But we do know the final height, which would be 0. So just a quick note, we can set the 0 point for y anywhere we want. So I chose to put it at ground level, so we end up at y equals 0 at the end of this. But really, you can put it anywhere. So let me just show you an example. I could have said y initial is 150 meters and y final is 10 meters. As long as we're showing the rock falls 140 meters, we're good. Okay? All right, so what types of energy do we have to think about? Well, we're certainly going to have to think about kinetic energy because the rock is moving. And we'll also have potential energy, specifically gravitational potential energy, because the rock is moving under the influence of gravity. So we'll have mgy for that. There aren't any other forces that we need to worry about that are being exerted on the rock. It's just gravity, actually, because we assume no air resistance. Oops. Which means there aren't any non-conservative forces doing work on our system. That means mechanical energy is conserved. So if we did have air resistance, then we wouldn't be able to use this idea, but we can in this case. And so let's make a table of all the types of energy that we labeled here. So we have kinetic, we have gravitational potential, and we want to see what these are equal to in the initial state and in the final state to fill out the table. So initially, for kinetic, we have 1/2 mv initial squared. And in the final state, we have 1/2 mv final squared. Okay, for gravitational potential, we have mg y initial. And we could write mg y final here, but y final is 0, so just put a 0 for the final potential energy. That's our table. When we add up these two energies in the initial column, that's E initial. When we add up these two in the final column, that's E final. So this equation says 1/2 mv initial squared plus mg y initial equals 1/2 mv final squared. Now notice we have m in every single term, so you can cancel that out. You can also multiply by a factor of 2 on both sides. So the 2 factors cancel out where you see a half, and now we have a 2 in front of g times y initial. So we're left with v final squared equals v initial squared plus 2g times y initial. So to get that final speed, simply square root the expression and plug in 25 meters per second for v initial and square it. And then we have 2 times g, which is 9.8 meters per second squared. Y initial is 140 meters. So by using conservation of mechanical energy, we were able to determine that the rock is moving at 58 meters per second when it reaches the bottom of this cliff. Okay, so that's it for this video. We're going to continue on with this Chapter 8 lecture in the next video. So I'll see you then. Until then, take care. See you later.